Hi everyone, let's go ahead and continue our discussion on circuits in series and parallel and start talking about the combination of both of those. So what we do in this case when we have a complex circuit is we need to start breaking it down into components that look more familiar to us. So for example, this is a circuit with items that look like they are in series, and then items that look like they are in parallel. So again, we're just looking at resistors in this case. We'll look at capacitors towards the end of this lecture, but for now we're going to look at resistors. And here we can see something that looks like a parallel circuit. Same thing here. We see something that looks like a parallel circuit, okay? So let me just go ahead and kind of outline those guys. So in that one looks parallel, and so that's why we have something called R sub P. And then this guy here, again, looks like something in parallel. So we can call it R sub P1, or maybe 2. We can call that one 1 and this one 2, okay? Just so that we can separate the two. But they are both in parallel. So then what we can do is find out those total resistances using the forms that we just saw, or formulas that we just saw. And then from there, we will get something that looks like this. So now we have two resistances, or two resistors, sort of, and this is representing these three resistors in parallel. Okay, so this is the same as this. Okay, so this is RP1 and this is RP2. Okay, now we have these two guys, these two resistors that are in series. Okay, R sub S, right? So these two are in series, so we can go ahead and combine those to get a new resistance. Okay, so those ones we just simply add when they are in series. Then again, we have two resistors in parallel. So now we have another R sub P, and I'm going to call that R sub P3. This is our third case of parallel resistors. Okay. Then once we find that value, that's RP2, or 3, sorry, right? And once we find that, then we have, again, two resistors that are in series, and then we can combine those to find our total resistance overall. Okay, so this looks quite complicated, but once you start breaking things down, it becomes more simplified and more straightforward, okay? So again, you're going to look at these complex things, think, oh my gosh, but when you start looking at these, you can see the components that look very familiar to us, okay? So let's go ahead and do an example, okay? So the figure that we just looked at shows resistors from the previous two examples wired in a different way, a combination of series and parallel. We can consider R1 to be the resistance of wires leading to R2 and R3. Okay, so did I forget to add the image? I wonder, oops, wrong thing here. Give me just a second, guys. I just want to make sure that we've got this Okay, yeah, so I forgot the image. Ah, where'd it go? Okay, so this is what we're looking for. Or this is what we have, sorry. Let's just go ahead and pull this guy out. Okay. We can do this. Nope, too much. Sorry, bear with me, you guys. There we go. Okay, so we have this circuit. Sorry, losing my train of thought here. So we have this circuit, and we have our voltage being applied. We have R1, R2, and R3. And we are trying to, well, we're going to answer these questions. So the first one is going to be find the total resistance, and then find the voltage drop, find the current through R2, and what is the power dissipated. So let me go ahead and redraw this in our PowerPoint. So let's go back there. Whoops, we have our voltage being applied and to a resistor R1, then splitting off into two other resistors, R2 and R3. And I believe that is all. Whoops. Okay. Let's double check here. Yes. So we have R1. Oops. Click. Oh, okay. Well. Okay. We have R1, R2, and R3. R1, R2, R3. And these were given in the previous two problems that we looked at. And same with our voltage. So let's just write that down again. So our voltage was 12 volts. R1 was 1 ohm. R2 was 6 ohms. And R3 was 13 ohms. And I think that's all we are given, if I remember correctly. Can double check here. Yeah, okay. Okay, so our first step is to find the total resistance, and that's going to be our overall resistance of the entire circuit. So we're going to need to start breaking our components down like we just saw, okay? So we need to break this down so that we get something that will be like this. Okay, so that would still be R1, and this would be, we can call it R2, 3, since it's a combination of 2 and 3. Then we will get our total resistance. Whoops, that's a little off, but you guys get the point. Okay. All right, so our first step is to find R2, 3, and these are in parallel. So R2 and R3 are in parallel. Okay, so we'll need to use the equation 1 over R23, that's our parallel resistance, is equal to 1 over R2 plus 1 over R3, okay, or 1 over 6 ohms plus 1 over 13 ohms. And let's see what that will give us. 1 over 6 plus 1 over 13 That'll give us 0.244 over ohms. And then again, we take our inverse. So R23 is going to equal the inverse of 0.244 over ohm. Okay. Oops. To the -1. So we get a total resistance of 4.11 approximately ohms. Okay, so now that's our resistance here. Okay, all right. Now we need to find our total resistance, and that is in series. So R1 and R23 are in series. Okay, hope you can read that. That made it worse. So R1 and R23 are in series, which tells us that R tote will equal R1 plus R23. And R1 is 1 ohm. R23 is 4.11 ohms, so that would equal 5.1 ohms. So that is our total resistance of this circuit. Okay. Now it wants to know what is the voltage drop in R1. Or in the textbook, it just says IR drop, which I times R is just voltage. So the wording is kind of weird in the textbook, but it's just the voltage drop. Okay. So we want to know what is this voltage across R1. Okay, so we know the resistance. We know, we don't know the current. Okay, let's see. Let me see here. If we have, I think that's what it's wanting. Give me just a second. Oh. All right, so we will first need to figure out our current, our overall current, as if we have this situation. So let's go ahead and do that. So B, for current, V equals IR, or I is equal to V over R. And this is going to be our overall total current. Okay, so this is, I'm going to just point that out, total current. And our overall voltage we just found, I'm sorry, we were given as 12 volts. So 12 volts over the resistance that we just found, our total resistance, or 5.1 ohms. So our overall current of the system will be 2.35 amps. So this is going to be our total current. But we're trying to find the current at R1. So we're going to do this, something very similar. or no, we're trying to find the voltage at R1, right? Yeah, the voltage drop. So V1 is equal to I times R1. Yes. Okay, so total current, 2.35 amps. And the reason that the current at that point is equal to the total current is because that piece, that resistor, is in series with whatever else is going on. Okay, so when we break it down, R1 is in series with another resistor. Okay, hopefully that makes sense. So our current remains the same in series. Remember that. So current remains the same in series, but in parallel, it will be different. So current stays the same. And we talked about this when we were talking about series circuits and parallel circuits. Okay, so our current is the same as the total current, or the overall current, times R1, which is just 1 ohm. So our voltage is 2.35 volts at R1. So voltage drop at R1. Okay. All right. So now we want to find the current through R2, or the second resistor here. Okay, so current through R2, that will be so this is our current, I, and that will split off into two separate currents, I2 and I3. Our voltage, we can find our voltage. Yeah, so our voltage drop in parallel will be different. Right? Let me go back to our parallel to double check. Oh wait, no. Here we go. Okay. Okay, so to find that current, we need to make note that for our parallel circuit, the overall, or the voltage of each resistor in parallel is the same. Voltage is the same. Okay, so let me show you what that means. So we're looking at the resistor here, and then that's it here. So just for simplicity's sake, I'm just going to draw that. So this is my R1, and it has some voltage that we just found, right? We have an overall voltage that was applied V. Okay, so in parallel in a parallel circuit. The voltage is the same throughout, and in series, so V is same. In series, V is equal to V1 plus whatever this other V in parallel is, okay? It's usually like V is equal to V1 plus V2 plus dot, dot, dot. In our case, we can call this VP. This will be VP, okay? So VP, the voltage for each of those is going to be the same, okay? So using this idea, we can solve for this voltage. So voltage P is equal to V minus V1, our overall voltage that was applied, minus the voltage that we just solved for. So 12 volts minus 2.35 volts. Okay, and if that wasn't quite clear, let me know and we can talk about this a little bit more in class, in person. Okay, but this is where it can get a little bit confusing, but this is the most confusing as it'll get for us. Okay, so 12 minus 2.35, and we get a voltage of 9.65 volts. So this is the voltage of these parallel resistors, okay? Remember that in parallel, resistors will have the same voltage applied, okay? Okay, so that's for that, but we are looking for the current through that resistor. So now we have our voltage, and I, or our current, is equal to our voltage, V sub P, over R2, since that's the one we're looking for. Okay, so we've got 9.65 volts over our second resistor, which is 6 ohms. Yes, 6 ohms. So we have 1.61 amps. So that is our current at R2. So this is R2, R3, okay? All right, next part here. What power is dissipated by R2? Okay, so power is equal to I times V, I believe. I'm going to quickly go back to double check, because that's not something that I remember off the top of my head all the time. Yes, power is equal to IV. Okay, so if we're looking for the power dissipated by resistor 2, yes, okay. 2. So that will be our current that we just found, 1.61 amps, times our voltage across that resistor, which is this guy here, this 9.65 volts. 9.65 volts. Whoops, 1.61 times 9.65, and we get 15.5 watts. Okay. All right, so this is a little bit more of a complex example, but we will do a lot of practice with these. Okay. All right, so this is a bit of a problem-solving strategy, and this is in the textbook as well, but I tried to kind of simplify it. Your first step is going to be drawing a very clear diagram and labeling everything that we know or want to know, okay? So that would be like what I was doing in the last one, drawing some sort of circuit diagram to show everything like the voltage, the resistors, and how they are, or are they in a parallel or series circuit form, okay? Then your next step would be identifying the unknowns. So what are you looking for? Determine whether the resistors are in series, parallel, or a combination. So again, after having that diagram, a lot of times it'll be given to you, so I would give you that diagram, but you will need to probably label the resistors, the voltage, and so forth, okay? Use those lists of major features for series and parallel to solve for unknowns. So that was the whether or not we're looking at series, is that going to have a current that is all the same throughout, or do I need to add them up? Is the voltage the same throughout, or is that something I need to add up as well? So those will all be things that we need to remember, okay? And then check to make sure after you solve for your unknowns with those equations that you create, if they are reasonable. So do the units make sense? Remember that resistance is greater in series than in parallel, and power is greater in parallel than in series, okay? So just a few things that'll kind of help get the ball rolling with these problems, okay? So I'll quickly talk about this, but this I'm going to kind of be real brief with, but there's something called electromotive force. It's not really a force at all, but we still use it. It's actually the ideal voltage supplied by a battery. So what we've been looking at is really the ideal voltage. So if we have a 12-volt battery, that is the ideal voltage, okay? And it's actually just the potential difference of a source when no current is flowing, okay? Now, if we have anything that's less than this ideal voltage, we call that terminal voltage, and that's measured with measured voltage between terminals of a battery, okay? And that will be less than your ideal voltage, okay? So we're going to stop there, and then we'll continue with Kirchhoff's laws and go from there. All right.